Hey, this is Mr. Ayton. Welcome back to Pre-AP Chemistry. This is Unit 8, Stoichiometry, and we are in Week 15. And what are we going to take a look at in Week 15 is limiting reagents or limiting reactants. We just went through a bunch of stoichiometry in Week 14, and well, we're going to take a look at the next step, which is limiting reactants. And the best way I know how to teach limiting reactants is human mutilation. There's a whole bunch of different human mutilation. There's a whole bunch of different models, like baking models and making sandwiches. No, my students understand human mutilation more than anything. So what is a limiting reactant? A limiting reactant means one of these reactants is going to run out, which we call the limiting reactant, and one of them will be in excess or will be left over. So if you can see in this reaction, we have two hydrogen gases, and I want you to focus on that two, reacts with one oxygen gas to make water, okay? And you're gonna run out of something. So let's say we have 10 moles of hydrogen gas, or let's model that as 10 fingers of hydrogen gas, and we have 10 moles of oxygen gas, or 10 fingers of oxygen gas. Well, look at your molar ratio. We're gonna be using 2 hydrogen gases for every 1 oxygen gas. So let's make it seem like every minute I'm going to cut off 2 of this person's fingers. And every minute I'm going to cut off only 1 of this person's fingers. So here we go. Ready? Human mutilation. Ready? At a Christian school. Yes. So 1 minute goes by and gone. Right? 2 minutes goes by. 3 minutes goes by. 4 minutes goes by. 5 minutes goes by. Who has run out of their fingers? This guy, right? This is what we call the limiting reagent. The oxygen gas is in what we call excess, what's left over. And once you're done with one of your reactants, your reaction's done. It's over. Because you need this and you need this to make water. So if we've run out of hydrogen gas, that basically tells you how much hydrogen gas you can, how much water you can actually make. So you can see in this model, we've run out of the hydrogen gas first. That's what we call our limiting reagent. So let's put this model to the test, okay? Let's take a look at this reaction. We have the same number of moles of aluminum and the same number of moles of chlorine gas, okay? And we have 2 moles of aluminum, 2 moles of chlorine gas. So think of that like fingers, right? And think of that like the same number of fingers. And look at your reaction. We're using 2 aluminums for every 3 chlorine gases. So whose fingers will we run out of first? Will we run out of aluminum's fingers or chlorine gas's fingers? We're going to run out of chlorine gas's fingers, aren't we? Chlorine gas is our limiting reactant, which means aluminum must be in excess. We're going to have this left over. So chlorine gas is our limiting reagent. It's our limiting reactant because we're going to use 3 of these chlorine gases for every 2 of the aluminum gases. So we're going to run out of fingers first, which means whatever's your limiting reactant is what is generating the entire stoichiometry of the entire problem, which means now we can do our stoichiometry. Remember, this number right here, this 2 moles of aluminum is not real. This is an excess. This is not real. So the 2 moles of chlorine is governing everything else, which means now I can do kind of molar ratios. For every 3, we're going to make 2. So 2, if you don't see it, we can do cross multiplying. 2 times 2 divided by 3. That means I'm going to make 1.33 moles of aluminum chloride from the 2 moles of chlorine gas, because that's my limiting reagent. Which means, think of the same ratio, 2, 2, 1.33, which means we're only using 1.33 moles of the aluminum. This is what we're using because this comes from your limiting reagent. Do you see how if we had 2 at the beginning and we only use 1.33, do you see how we have 0.67 moles of aluminum left over. It is in excess. So once you find the limiting reagent, your limiting reagent will determine what happens in your entire reaction, okay? And you can use kind of the human mutilation fingers theorem to generate that. Now, if you're in grams, we have to take a look at grams and we have to put this in the moles, because remember, the fingers theory, the fingers model is a ratio of moles. We're looking at moles, so we're looking at a count of something. So we have to take 10 grams, even though these seem like they're on the same playing field. They're not, because when we divide by magnesium's molar mass, which is 24.3 grams per mole, so 10 divided by 24.3 grams per mole ends up becoming, how many moles do I have, is 0.41 moles of magnesium, okay? Let's take a look at the oxygen gas. We're going to divide by oxygen gas's molar mass, which is 32 grams per mole, and 10 divided by 32, I'm doing that on my calculator, I get 0.31 moles of oxygen gas. Now, do you see how we don't have the same number of fingers to begin with? We have 0.41 and 0.31. Magnesium, we're using twice as much as the oxygen gas. Remember, it's a 2-to-1 ratio. So we're using twice as much magnesium. Which one are we going to run out of first? We're going to run out of the magnesium first, aren't we? The magnesium is our limiting reactant, which means the oxygen gas is in excess. And so once we know this, that's the true number. That's going to give us everything in my chemical reaction. Once you know the limiting reactant, you're going to use that for everything in your chemical reaction. So let's do a molar ratio. 0.41 divide by 2. 0.41 divided by 2 ends up giving me 0.205 moles of oxygen gas is what I've used. I didn't use all 0.31 because it was in excess. Okay? And I can know how much magnesium oxide. Take a look at your ratio. 2 gives you 2. 0.41 gives you 0.41 moles of magnesium oxide. Okay? And so you can see, now I can come back to mass, can't I? By multiplying by the molar mass. Well, I can multiply by 24.3 grams per mole, and that gives me 10 grams of magnesium. You can see oxygen is times by 32. So we have 0.205 times by 32. Means I only used 6.56 grams of oxygen gas. Did I use all 10 grams? No, I only used 6.56 because that was in excess. That was in excess. And then I'm going to multiply by magnesium oxide's molar mass. 24.3 plus 16 is 40.3 times 40.3 grams per mole. So 0.41 times 40.3 ends up giving me 16.56 grams of magnesium oxide. And take a look. You have a conservation of mass, don't you? 10 grams of magnesium reacts with 6.56 grams of oxygen gas. Not all 10 grams. You can see you got like 3.5 grams left over, don't you? And that's going to make a total of 16.56 grams of magnesium oxide. So that is our limiting reactants for stoichiometry. I hope this helped. Don't go cutting off your fingers. Just do it in stoichiometry. See you guys. Bye.